And I apologize, you'll see some of the videos and slides that I've shown before, but these are central to my story. So what I'm going to show you is a time-lapse movie of the Milky Way that my friend John Rockman, a physics teacher in Palo Alto at Castlear School, put together. He set up a digital SLR camera in a game park in Kenya. This is not far from the equator. And he took a series of 30-second exposures. I think there were 25-second exposures, but they were separated by 30 seconds, something like that. Maybe I'm getting that wrong. But you can see the Milky Way in this view. And I removed the label because I don't want to distract from the movie. But you can see the Milky Way quite clearly in this picture. It's low in the sky. You can see a tree here. It's lit up by human-made lighting. As the video plays, you'll notice the sky getting darker because it's getting further away from sunset. The sun is sinking further and further below the horizon. You can see it getting darker. And at some point, you see lightning, shooting stars, clouds right there. Someone will turn off the lights there. The tree isn't visible anymore. Lightning again. And this is, of course, this grand sweep, this apparent grand sweep across the sky is caused by the rotation of the Earth. And this is our home, the Milky Way, that's appearing to sweep across. I say appearing to because it's really because of the Earth's rotation. And you can see that very clearly in this version of the Milky Way video. This was put together by Arya Narenberg, and he used a special camera mount to keep the sky frozen in the camera's frame with time. As the sky appeared to rotate because of the Earth's rotation, this camera compensated for the Earth's rotation. So I'll again remove the label. You'll see planes flying overhead. You saw a plane go by right there. The electrical wires. There's another plane. This to me is a remarkable video showing you what the effect really is as opposed to what the effect appears to be, which is talking about the rotation of the Earth. Okay. I'm, of course, preaching to the choir when I talk to an astronomical society about the rotation of the Earth. All of you take deep sky photographs, or you follow the sky, so you know that the sky appears to rotate around the pole star in the course of the night. Here's another view of the Milky Way taken from the southern hemisphere. You can see the Southern Cross in the picture. If you can see my cursor, this sort of kite-shaped constellation is the Southern Cross. And this right here is the Carina Nebula. And I'm going to show this in detail because this became a target for the James Webb Space Telescope. At one point, James Webb focused its cameras on a portion of the Carina Nebula. And this image you're seeing here is from an astrophotographer, Kiko Fairbairn, wide-angle image. If anyone knows any of the photographers I mentioned, please put a shout out in the chat. I'm not familiar with this person, but I found this image. And in the next image, we're going to zoom in to another astrophotographer's image, this time just of the Carina Nebula. So in the next image, you'll just see what's inside this red square. So just what's inside. Again, I'll go back and forth. And this one is taken by Harold Boren. Again, it's a ground-based astronomical photograph. And in the next image, we're going to zoom in on a section up here, section of the nebula up here. And these are clouds of gas and dust that are lit up by ionizing radiation from nearby stars. That's ionizing the gas, causing the electrons to first escape and then cascade back down and produce. You're seeing a mixture of H-alpha light and other Balmer lines. Now, if we zoom in to this section in the upper right, this is also a ground-based image, now taken with really an excellent telescope in Chile, the European Southern Observatory Telescope. This is a research-grade telescope that's used by the European astronomy community. And this is a portion that's called the NGC 3324 Nebula. And you'll see another rectangle here. We're going to zoom into this rectangle. And I'm going to zoom but rotate so you can see this rectangle in horizontal configuration. And I'm going to show you 3 images, all taken from space, one with Hubble and 2 with, three images. One is this image itself, taken from the ground, compared to the Hubble image, compared to the James Webb image. So, ready? So there's that section of the cosmic, this has been called Cosmic Eclipse. This is, again, European Southern Observatory, ground-based from the Chilean Andes. You can see sort of this edge to the nebula. You can see stars. They look sort of blurry compared to the Hubble image of the same thing. Image looks a lot sharper. This edge looks a lot sharper. The stars look sharper. You can see this faint nebula here, but see so much more detail over here. And you see patches, dark patches of where dust is blocking the background light. You're seeing this dust in silhouette. Now, in going from the Hubble image to the James Webb image, this is an infrared image. Infrared travels more easily through dust, so you don't see these silhouettes anymore, not as clearly anyway. And you get a whole other level of sharpness. And an easy way to see that is just focus on this edge here. You know, this edge it's sharp, but it looks razor sharp over here. And the other way to see the sharpness of James Webb is look at the number of stars in this region that I'm using my cursor to point to. Compare that to the number of stars seen in James Webb. Now, part of this is because the James Webb image is further in the infrared, so light is shining through better. But it's bigger, the bigger telescope, sharper images, better diffraction limit. We're going to zoom in next into this little thumb that's sticking out. And again, 3-way comparison, ground-based image at the top, Hubble and James Webb. And you can see the striking difference in the number of stars and the detail you can see. There are even these 2 stars here, right against this nebula, right against this, you don't see them here in Hubble, you don't see them from the ground, but you see them in the Webb image right there, those 2. Spectacular, just the level of detail is spectacular. And you've seen this, I'm sure you've seen images of, these and other images from James Webb, but these famous cosmic eclipses really caught my attention. And this tiny little thumb is, of course, much bigger than our solar system. Inside it, stars are forming with planetary systems and accretion disks around them. Now, I wanted to show you this image. I want to switch gears and show you a ground-based image. And if you stare at this image, you'll notice that some things are blinking. And now that I mention it, you can probably see there are lots of things blinking. There are these 3 stars over here that are blinking. This one, and this one. There's one that's blinking right next to this bright star. There's one blinking at the edge of this bright star. You can barely see it. These 2 are blinking right there. This one down here. And you can't measure this, but these blinks are not synchronized. When some stars are getting brighter, others are not. This is a time lapse, and it looks like a looping time lapse. And at some point it is looping, but each of these stars loops. Each of these stars loops with a different period. It goes up in brightness, down in brightness, up in brightness, down and the periods range from 6 hours, so a quarter of a day, to 3/4 of a day, 18 hours. These are stars called Aralari stars. In fact, this particular cluster of stars is Messier 3, M3, and you're seeing a time lapse of the Aralari in this cluster. Now, the beautiful thing about Aralari is they're easy to spot, right? I mean, you can tell them apart from the other stars in this cluster because they are very clearly pulsing. And you can also see that they mostly have the same color. They're sort of bluish white. And you'll have to take my word for this. Their average brightness is the same from star to star. So even though this is, pulsing up and down, if you take its time average brightness, that's the same as the time average brightness of this star, this star, this star. Now, these stars are all the same distance from us. So when I say their time average brightness is the same, their time average luminosity, that means their intrinsic brightness, is the same from star to star. That makes them very powerful because once you have something called a standard candle, something whose time average brightness is the same from one star to another, you can easily use them to measure distances. You can easily use them to tell how far away they are. You just have to monitor them through the full cycle, measure their average brightness. From M3, you know how bright they are intrinsically. You see how bright the average brightness, you see how much the average brightness appears to be from our perspective, and that tells you how far away the star is. So they're excellent distance tracers. And if we want to study the outskirts of the Milky Way, which my PhD student and I are doing, this is of course, an artist's view of the Milky Way. And, on the scale of the Milky Way, of the disk of the Milky Way, the sun would be located somewhere about halfway from the center to the edge, right? This is not as you know, this is not a 2-scale picture of the sun. The sun doesn't actually look like that. It's just a representation. And the sun and solar system are located about 25,000 light years from the center of our Milky Way. Okay, so that's about how far our entire solar system is relative to the center of our Milky Way. Now I'm going to remove these symbols and turn our galaxy on its edge and shrink it just to fit everything into the page. So I can show you a map of how far away from this galaxy we've discovered Arillary stars. Okay, these Arillary stars were discovered by my PhD student, Yuting Feng, and we're studying them with the help of one of my other former PhD students, Emily Cunningham. Again, remember the diameter of the disk of the Milky Way was about 100,000 light years. These things that we found are up to 1 million light years away. You can see that here, 1 million light years away, about 40 times the distance of the sun from the center of the Milky Way. We're super excited about this. We're going to be presenting, Yuting is leading a poster at the American Astronomical Society meeting. The American Astronomical Society has 2 meetings a year. Their big meeting is in January. Big meeting. It's every year it happens. It's the biggest professional astronomical society meeting of the world. So this is going to happen in Seattle from January 8th to 12th. We are probably going to do a press release on this discovery. You can see that these stars, I don't know if you can see the scale here, or actually the scale isn't marked here, but these distant stars are about 1 million light years from the center of our galaxy. This work is redefining, or defining, I should say, because this is really uncharted waters. It's defining the outer limits of our galaxy. Now, tomorrow night, Yuting, Emily, a couple of others, Doug and Eric and I, are going to be using the Keck telescope to get spectra of some of these objects. So this is 300, this is 250, 200, 150. We'll be studying a bunch of stars in sort of this distance range where my cursor is. About halfway out to the edge, okay, and not all the way into the center, but just things that are of intermediate distance. Say these things that are this far away, they're too faint for us to get spectra in any reasonable amount of time, even with the world's most powerful telescope. We're going to be using the Keck telescope tomorrow night, Saturday night, Hawaii time. By the time we are offering a Shadow the Scientist session, but it'll be quite late at night. It'll start at midnight California time. But of course, I'm speaking to amateur astronomers, and it'll be a Saturday night. So hopefully you'll join us for this. And I put a link in the chat that I'm happy to share again.
And Professor, I think you mentioned this. I think you may have answered it already, but I was just thinking. I put it in the chat room.
Yeah.
Isn't 1 million light years? That's halfway to Andromeda. Isn't that outside the Milky Way?
Well, it's defining the Milky Way, right? I mean, it's not out, it's outside the disk of the Milky Way, but we think this is the halo of the Milky Way. And it's not quite halfway to Andromeda. Andromeda is about 2.5 million light years away. So it's practically halfway.
Okay.
And now, mind you, these stars are not in the direction of Andromeda, but people are finding, us and other people are finding these stars in any direction they look. And you can see from this map here that sorry, I'm going to post the Shadow the Scientist thing in the chat for those who just joined. Let me just, sorry. I didn't mean to put host observatories. I don't know why that showed up. My bad, sorry. I'm just trying to put something in the chat here. No, it's not letting me do that. But anyway, the Shadow the Scientist link is something that I was hoping to put in the in this chat here. So it's https shadow.ucsc.edu. This is the website for Shadow the Scientist that we'll be running tomorrow. Okay, so coming back to the my PowerPoint slides. Where did they go? So tomorrow night we'll be taking spectra of some of these stars. You're welcome to join us. It's sort of it's work at the cutting edge in more ways than one. This is really, as you said, Raj, it's defining what we think the outer limits of our galaxy to be. Our outer limits of the galaxy are beyond this, because we are finding stars out to this distance and there's no hint of a break. But you can see from here that the density of stars falls off with increasing distance. There's a higher density of stars closer in than further out. But if you plot this on a plot of log density versus log radius, it looks like a straight line. There isn't a sharp downturn we've detected yet. So we haven't found the edge of our galaxy yet in this sense. Okay. Does that answer your question, Raj?
Yes, absolutely. Thank you.
Thank you. So, of course, Raj mentioned the Andromeda Galaxy. I've been studying it. This is a digital mosaic that my colleagues and I took of Andromeda. We took this image 30 years ago, 1992. And at that time, it was the first digital mosaic, not a single image, but a mosaic. And you can sort of see the scalloped edges of the mosaic. It's 4 different versions of the same mosaic at different contrast levels. And my students and I have been using this to study the cannibalism of these small galaxies by Andromeda. And this is a wonderful Robert Gendler image of Andromeda with 2 of its satellites, M32 and NGC 205. And last month, I was out at the Keck telescope in Hawaii, pounding away with the DEIMOS spectrograph to get spectra of stars in and around M32. And I'll show you a map of what we were doing last month. I was in Hawaii for 2 weeks. We had 10 straight nights on the Keck telescope. And the Keck telescopes are gradually appearing into view. This is a Mauna Kea sunset imaged by Laurie Hatch, a dear friend and an amazing photographer who used to live up at Lick Observatory until a few years ago when she and her husband retired. I have to share this James Webb image with you because, if you look at one of these satellite galaxies of Andromeda, they look like a cloud of light. But with James Webb, they resolve into individual stars. And this is a picture of a group of people inside a planetarium looking at a James Webb image on the planetarium screen. The way you know it's a James Webb image is look at that hexagonal pattern producing 6 diffraction spikes. This is the hexagonal segments of James Webb. And these people commented that we felt like we were inside the galaxy. It really, well, one of them has stars shining on his back. So really, it does feel like they're inside the galaxy. Remarkable image again.
And what does WLM stand for?
That's the name of one of the galaxies. This is the name of the galaxy whose image James Webb has taken.
Okay.
WLM is the name of one of it's a small galaxy within the local group of galaxies, within, orbiting sort of Andromeda and the Milky Way.
Okay, thanks.
And here's Andromeda again, and that white sort of crime scene outline is what's been imaged by our team with the Hubble telescope. I showed you that mosaic before. I showed you this mosaic before. And this was a mosaic of 57 images in blue and infrared light, 57. And at that time it was a state-of-the-art mosaic, 57 images in 2 filters. Now with Hubble, we've taken 3,000 images and mosaic them together. And I say it's a big team. We spent 4 years doing this, 828 orbits of Hubble around the Earth in 6 filters. Images are taken in 6 filters, 2 ultraviolet filters, 2 visible light filters, 2 near-infrared filters. This was a large project that was run by my dear colleague, longtime collaborator, Julianne Del Canton. She's now the director of the Center for Computational Astrophysics in New York. She used to be a professor at University of Washington. And our group at Santa Cruz has gotten spectra of stars that were imaged by Hubble. And just for scale, this is the full moon to scale on the upper right. And Andromeda is not small. It's big. It's bigger than the full moon. Just has low contrast. So you need binoculars or high contrast, or digital image where you can crank up the contrast to see the details. So what we'll do next is zoom into this crime scene outline. I'm sure I've shown you this movie before. This is zooming into Hubble's image of Andromeda. But for me, this never gets old. So I'm going to show this one more time. And there's Andromeda, 2.5 million light years away. This is the arc of the Milky Way, band of gas and dust, stars, of course. And as we zoom in, you'll see the satellite of Andromeda. Andromeda's other satellite is down here, M32, NGC 205. And we'll zoom in so far that you'll be able to see individual stars in Andromeda. And this is as revealed by the Hubble Space Telescope. I can watch this movie again and again. This is a blockbuster as far as I'm concerned. And this is now the largest digital mosaic that Hubble has ever taken, and it happens to be of Andromeda. So my professional journey around Andromeda has come a full circle. First digital mosaic and now the most recent digital mosaic. And these dust clouds are, they're blocking light. That's why they look dark, not because there are no stars there, but just like clouds can block the light of the sun on a cloudy day, these giant clouds are blocking, interstellar clouds are blocking the light of Andromeda stars. You'll also notice that the stars around these clouds look very red because when stars shine through dust clouds, the blue light gets absorbed and scattered and the red light shines through. So the stars look redder than they actually are when you see them through clouds. Just like the sun looks red, a sunset looks very red on a hazy day because the blue light gets scattered away from us, the red light gets through. I did want to show you this. I don't think I showed this to you before, but this is something we're getting ready to do next year. Again, this is Hubble. This is one of the sections of Hubble that was imaged by the Hubble telescope. These are brightnesses, and brightness on the y-axis, and color, which is sort of indicative of temperature of stars as measured by Hubble. This is called the red giant branch, going up to here where this upper end of this trapezium is. That's a red giant branch. These are called intermediate age asymptotic giant branch stars. This is red giant. This is called the red clump. These are individual stars in Andromeda for which brightness measurements have been made. This is how bright they are in the infrared. 160 is the 1600 would be the wavelength in nanometers. So 1.6 micron light is what Hubble is measuring here. And on the x-axis is something called color, where you're looking at how bright the star is at 1100 nanometers, and subtracting from that how bright the star is at 1600 nanometers. So 1.1 micron, 1.6 micron. If you do infrared photography, this is like the J and H bands. These are filters that exist, J and H bands. This trapezium marks stars for which we're going to get spectra with the James Webb telescope. And we've been approved to get, I'm part of a team that got some time with James Webb in cycle 1. Cycle 1 hasn't started. They're still doing early release observations, early release science. Sometime next year, James Webb will start its cycle 1 year of observations, and these observations will be taken then. This is what we hope to learn. We hope to get spectra. And in red and black are 4 different spectra, stars of the same temperature. These are model spectra of stars of the same temperature, 3750 Kelvin. Stars of the same log G, that means they're both, in both cases, these are red giant stars. Stars of different ion composition, Fe over H of -1, Fe over H of 0. Astronomers, professional astronomers, will often use a logarithmic scale to measure the ion to hydrogen ratio. It's a logarithmic scale relative to the sun. So when you see 0, it means it's the same as the sun. That means the ion to hydrogen ratio of the sun, of the star, divided by the ion to hydrogen ratio of the sun, the logarithm of that is 0. The logarithm of something is 0 when the ratio is 1. That means this is equal. This star has an ion abundance, ion to hydrogen ratio, that's the same as the sun, whereas this star over here has an ion to hydrogen ratio that's 1/10 of the sun, much more anemic. And if you look, just compare these two regions, this is much more cut up by ion absorption than this one is. This dip is much more prominent for sun-like star than it is if the star were much more anemic, 10 times more anemic. The red and black distinguish between other elements. Alpha elements refers to light elements like calcium, magnesium. What am I missing? Titanium. I said calcium, sodium. So light
These are what they
elements.
call metal poor stars?
This would be considered a relatively metal poor star. This would be a solar metallicity star.
Okay. So
So
metal poor stars are the oldest stars, is that correct?
they can be. There's sort of a rough correlation with age, but it also depends on the environment. So within the Milky Way, at a given age, there's a range of metallicities depending on the environment in which things formed. So in general, over time, clouds of gas and dust tend to get enriched by iron that's produced in supernovae. And when those supernovae explode, this iron gets injected, gets injected into these clouds. So yes, over time, in general, the iron content of clouds goes up, but it's not a uniform process because clouds have different densities. Supernovae may be going off in different parts, not quite uniformly. So if you see what I mean, there's a general trend of the iron abundance growing for clouds out of which stars form, but at any given time, there's a big spread of iron abundances. The mean keeps increasing, the mean iron to hydrogen ratio keeps increasing, but any given time, if you take a snapshot, different clouds will have a range. Does that make sense? Does that make sense?
Yes, yeah, that's why I gave you the thumbs up.
Oh, thank you. Sorry, I have it all minimized, so I'm not seeing any of the action. Sorry. Thank you. Okay, so this is exciting for us. We're waiting for this James Webb observations to come out, and we'll write papers based on these data once they do come out. I told you I went out to Keck last month. This is Andromeda. This grayscale image in the background is an ultraviolet image of Andromeda. This is a zoomed out view where you can see the center of the galaxy, the disk. This is M32. This is NGC 205. I'm going to focus on not the inset, but the main image. We have a new program with Hubble that is now doing a mosaic of the southwestern part, the lower right. The previous mosaic I showed you that we zoomed in is off the camera, it's off the screen here. It's in the upper left. So we already imaged the upper left. Now we're imaging the lower right. This is one of the biggest Hubble programs, not one of the, it's the biggest Hubble program in the current cycle. And all of these very thin lined bricks, these haven't yet been imaged by Hubble. It's going to be a 2 or 3 year program, 2-year program. This hasn't yet been imaged, but in the first 2 cycles, first 1 year, 6 months apart, Hubble has taken images, and those are the parts that are marked in bold black. Okay, so in bold black, these images have been either completely or partially imaged by Hubble, and the light gray rectangles haven't been imaged yet, but will be in the course of the next year or so. Now, I designed this pattern of these funky shapes. Each of these shapes represents the field of view of the DEMOS spectrograph on the Keck telescope. That's not the spectrograph we'll be using tomorrow night. Tomorrow night, we'll be getting spectra with a different spectrograph on Keck called ESI, and we'll be measuring RLR in the Milky Way halo. But in September, we were using the DEMOS spectrograph to get spectra of individual stars, both in and around M32, which is this galaxy here. And this beautiful Japanese, beautiful to my eyes, Japanese fan pattern means you can target these stars many times over while also covering different areas of Andromeda with the other end of the mass. That's why we I designed this as a Japanese fan. Okay, so moving on, this is the sort of details of some of the experiments we are doing right now. Now, I've shown you before that galaxies collide, and I wanted to show you a quick snapshot from, a quick video clip of 2 galaxies that are about to collide. And the reason I'm showing you colliding galaxies is that's what we're trying to study in Andromeda. M32 is colliding with Andromeda. These are real galaxies that are colliding. And back to the computer simulation, you remember this computer simulation takes you through a progression of 2 galaxies that are gradually colliding over billions of years. And this is relevant to us because, we're studying galaxy collisions in Andromeda. We're studying galaxy collisions between Andromeda and us. Okay, so while these 2 are intersecting, we switch to 2 real galaxies that are intersecting, and we go back to our computer simulation. And as they start to stretch each other out, we stop the computer simulation right there. And here are 2 real galaxies that are stretching each other out. We go back to the computer simulation. The main bodies are going to fall back together, and right before they merge, right about there, we stop the computer simulation, change our perspective. So you can see the 3-dimensional structure. And here are 2 This is a real pair of galaxies that are in the late stages of the collision process. The main bodies, again, back to the computer simulation, the main bodies are actually colliding now or merging now. Collision is not an accurate word, merging. Again, change our perspective. And here's a final pair of galaxies, real galaxies going through the collision process, very late in the collision process. Okay. James Webb has spectacular images of colliding galaxies. This is Stephan's quintet. Some of you may have imaged Stephan's quintet with your telescopes. 5 galaxies, 1, 2, 3, 4, 5. They're imaged with Hubble on the left, James Webb's near-infrared camera. NIRCam is near-infrared camera. This Hubble image is also in the infrared, by the way. Wide Field Camera 3 can take images in the ultraviolet or infrared, but this, I believe, is an infrared image. This is also an infrared image with near-infrared light. In fact, without really, if you ignore the color hue, these two images look quite similar. You see the same features. This double shell over here is this double shell there. This tail over here is this tail over here. This loop over here is this loop over here. You can see the two nuclei very clearly. You can see this sort of loop here over there. And now this is James Webb's images in the mid-infrared. MIRI is mid-infrared imager. Looks drastically different. For example, this galaxy's nucleus is the brightest in the mid-infrared, this nucleus. Doesn't look that remarkable in these images, these two images. It looks just as bright as the others, but in the mid-infrared, it really shines through. And this one's nucleus can't hardly be seen in the mid-infrared, this galaxy. So you can see the two nuclei here. You see this patch that's really bright in the mid-infrared, not so in the near-infrared. Sort of looks more ho-hum, ordinary. So I just wanted to show you some of these because galaxy collisions are also things that James Webb's images are contributing to. Collisions are not just happening in Andromeda. They're also going to happen between Andromeda and the Milky Way. The Milky Way is going through its collisions right now. And this is something, I think I mentioned this before, our group of the discoveries we've made, I would count our recent discovery of the extent of the Milky Way, Yuting's work on the RLRE in the outer parts of the Milky Way, to be one of the most significant discoveries that I've been involved in my professional career. 2 other discoveries. One goes back to 2005, so 17 years ago. Our group at Santa Cruz discovered that the Andromeda galaxy was 5 times bigger than people previously thought. People thought it was 30 kiloparsecs in diameter, in radius, and we found it to be 150 kiloparsecs in diameter. Another discovery that happened now 10 years ago, 2012. This was led by a group in Baltimore, but we were part of this group. We discovered that Andromeda is on a head-on collision with us. So put these two things together. We discovered in 2005 that Andromeda, that our neighbor is 5 times bigger than we previously thought. And then 7 years later, we discovered that neighbor is coming straight for us. So that combination is a bit scary. And it led us to conclude that the Milky Way Andromeda collision is inescapable. NASA put out this beautiful video, Milky Way, Andromeda, and they did a prediction of what the future will hold. Andromeda will get much bigger in the future. I say future, very far in the future, billions of years. And that'll lead to a collision ultimately between Andromeda and the Milky Way. Each is moving towards the other, moving towards our common center of mass. There'll be a giant burst of star formation when the two galaxies meet because there are gas clouds in both galaxies that will go through shocks and form stars. And finally, in about 7 billion years, the two galaxies would have merged into a single elliptical galaxy. So this is sort of one of the things we've been intrigued about, we've been studying. My group studies galaxy collisions, but understanding what's going to happen to our own galaxy and how it's going to collide is of great interest. Now, galaxies, when they collide, they form things like these, elliptical galaxies. And Raj, please give me a time check so I don't overstay my welcome.
You're doing fine. No problem.
Much time? How much more time do you want me to take?
As much time as you need.
All right. Okay. I will go through this. It won't take. I want to spend a little bit of time at the end talking about STEM research opportunities, and I want to talk about people as well, people who influence me. And okay, so this is a giant elliptical, M87, Messier 87, and you've got a supermassive black hole at its center. And we can study its effects. We can't see it directly. We can study its effects. And I want to be a little careful about what I mean by that. So we're going to zoom in here. And as we zoom in, these are star clusters that are going by. And at some point, the telescope loses resolution. You can't really see any detail. So we're going to switch to an artist's impression of what's going on in the supermassive black hole that's at the center. This is an artist's conception. This is not real images, not real video. So artist's conception is the swirling material, very hot material. That's what the white, yellow, and orange and red represent. White is the hottest. It's spewing out a jet of material. We can see the jet. We can see the effects of the black hole. We can see M87's black hole it's one of the most photogenic black holes because it was the subject of this picture, which is taken with the Event Horizon Telescope, radio telescope. This is now those, radio emission from that disk of heated material. When we see it on its way to us, it gets bent by the gravity of the black hole. This is Einstein's prediction that mass should bend space-time in its vicinity, and when light travels through that space-time, we should see what's called an Einstein ring. So this was imaged with the Event Horizon Telescope a few years before the pandemic. You can fair to call this the world's largest radio telescope because it consists of an array of telescopes, radio telescopes, located in different parts of the world. You can see some in Hawaii, some near the North Pole, some near the South Pole, South America, North America, Mexico, England, Netherlands. So it's a combination of telescopes around the world. An Australian telescope isn't being used in this one, but it's the Event Horizon Telescope. So black holes bend light, but that's not the only thing that bends light. Galaxies can bend light. And this to me is one of the spectacular images taken by James Webb. These arcs over here, this one, this one, this one, this one, these are pieces of a ring produced by the mass of galaxies in the foreground. Look at this ring. You were talking about the smiley face on that whale shark. That's what I was thinking of, this arc when you showed that image. These arcs, you can see they form pieces of a circle, even this one over here, even this stretching over here, this one stretched here. These, you can see very thin arcs over here. This is a mirage, light being bent, light of background galaxies being bent by the gravitational lensing effects of foreground galaxies, by this cluster of foreground galaxies. This is a particular cluster that James Webb has imaged. Now,
I object for the record. As you can tell by my background image, I took this picture.
Let me see your background image. Let me see this. I want to. Oh, wow. Is this the same image in your background? Yeah, I can see this.
Of course, yeah.
I can see this arc above your head.
Of course.
Wonderful. A spectacular image, really. But one of the things is it's a mirage. It's not. When I say mirage, I mean these two pieces. This piece that if you can see my cursor, this piece here and this piece here are really the same galaxy whose light has been distorted, and you see it imaged twice. It's almost like if I took a distorted piece of glass and I held it against, let's say, a period on a newspaper, like someone at the end of a sentence, there's a period, and I look at it through distorted glass, I might see 2 images or 3 images or 5 images of that period. And that's what this is, 2 separate images of the same galaxy. How do we know this? Well, James Webb has taken spectra as well of those same 2 galaxies, right? Those same 2 pieces. And if you take a spectrum, you'll notice that they have hydrogen and oxygen emission lines in exactly the same ratio and at exactly the same wavelength. In other words, they have the same redshift, these 2 pieces. And these spectra shown here, this is a kind of spectroscopy called GRISM spectroscopy. So this is a little harder to interpret, or this is a little difficult to explain what's happening here. But this dot right there, this dot is emission lines. These dots are emission lines right here. And conclusively, you can see that these 2 galaxies are at the same redshift. You do determine that through spectra. You do determine, Jerry. That's exactly right. So Doppler shift, connect that Doppler shift to the expansion of the universe. That tells you how far away these 2 pieces are. They're exactly the same distance from us. In fact, if you think about this gravitational lens, it's like nature's own telescope. It's magnifying, it's focusing light. So what people have done with James Webb is they have placed James Webb behind this cosmic telescope. So you can use the combined power of this cluster of galaxies whose gravitational lensing is acting like a cosmic telescope. You're combining that with the power of James Webb to study some of the most distant galaxies known in the universe. There's hydrogen and oxygen again. This is doubly ionized oxygen, something called O3, oxygen with 2 electrons removed. Their rest wavelengths are 5007 and 4959, and the wavelength of hydrogen beta is 4861. This is in angstroms. This is a hydrogen alpha. And you can see that for this particular galaxy, whose spectrum you see here, that's this galaxy here, its image is right there. You can barely see it in the image. This galaxy that's right here. So these are look back times. This galaxy is being seen at a certain redshift. You can see for this next galaxy, it's a higher redshift. This thing is the longer wavelength. And for this galaxy, the same pattern is at an even higher redshift. H alpha is off the charts here. And this one is at an even higher redshift. So with James Webb, you can see that these four galaxies are at successively large distances. That means looking further back in time, 11.3 billion years, 12.6, 13.0, 13.1. So these two are very close together, not close together, but they're about equally far away from us. This is slightly further away, 13.1 as opposed to 13.0. Now remember, the Big Bang happened 13.7 billion years ago. So this is looking almost all the way to the Big Bang, okay, with Webb. With the combined power, really, to be fair, combined power of Webb and this MACS cluster, MACS cluster. Now, this is the next image is one of the most spectacular images I've come across. Raj, I think you should make this your screensaver. This is that same image, but superposed on Van Gogh's Starry, Starry Night. I think this is a lot prettier than James Webb alone. And I bet Vincent van Gogh would have as big a smile on his face as that whale shark if he knew we were doing this. Vincent was seldom happy in his very difficult life, but I as an artist, I may not have told the group, but I am an artist. I've been an artist long before I've been an astronomer. So anyway, the artist in me loves this, the astronomer in me loves this. Okay. So just a quick timeline of the universe. After the Big Bang, there was inflation. There were quantum fluctuations, pre-inflation that became the macroscopic fluctuations because of rapid expansion. Quantum fluctuations got frozen into the fabric of the universe. Gravity took over to produce galaxies. One of the cool things is post-inflation, we can see the effects of the quantum fluctuations when we take radio images of the sky to study the afterglow from the Big Bang. So these are early ripples in the cosmic ocean. These are hot spots and cold spots. Dark blue and black are cold spots. Red and orange are hot spots. And when I say hot and cold, the differences of temperature are 1 part in 100,000. So it's almost perfectly uniform, but the cold spots are 1 part in 100,000 cooler than average. And the red points are 1 part in 100,000. In other words, 0.00001, 4 zeros and a 1. By that fraction, hotter than average. Okay. Now, the hotter than average pieces, of course, are also seen here. This is an 8-off projection of the afterglow from the Big Bang. And these hotter than average regions become infant galaxies that then collide to become large galaxies. Within it, there are stars. These stars are all vigorously producing elements of the periodic table in their interiors. The massive ones explode at the end of their lives. During the explosion, more elements are produced than during the life of the star. Out of those elements, the sun and planets were made out of those elements. Because the Earth contains these elements, there are complex molecules like proteins and DNA and RNA, and they're wonderful life forms. This is a picture of my daughter and son shortly after my son was adopted. My son is the one on the left. My daughter was, how old was she when this picture was taken? She was 7 years old. Delighted to have a brother, finally. Okay, I want to switch gears a little bit and talk about some people who've inspired me over the years. This part is very short. A lot of people have inspired me. Albert Einstein is one of them. Salvador Dali is another. Michelangelo is another. Albert Einstein, this is a photo from 1912. It's a close collaborator, Carl Schwarzschild. Carl's son Carl died when he was in his 30s, but his son was born in 1912 and followed in his father's footsteps, became an astronomer, got to meet Einstein in his childhood because Einstein visited Carl Schwarzschild and Martin Schwarzschild home after Carl Schwarzschild had passed away. Carl Schwarzschild died during World War I, so a few years after these photographs were taken. Martin became an astronomer at Princeton University, where he was one of my mentors. So one degree of separation to Albert Einstein through Martin, because Martin was my mentor and Martin was mentored by Albert Einstein and by his own father, of course. But now I met 3 other people in Princeton who got to know Einstein after Einstein moved to Princeton. And actually, maybe I'd met him at international conferences as well. But Martin is the only one I know who knew Einstein from his early days in Germany, and then also reconnected with him at Princeton. The other 3 people I knew at Princeton who knew Albert Einstein were Freeman Dyson, Lyman Spitzer, and John Wheeler. John Wheeler is Richard Feynman's PhD advisor. This is another person whose journey has crossed mine. I happened to go to a talk by Stephen Hawking in Santa Clara here in Silicon Valley. And again, the struggles he overcame are an inspiration to me. Here are 3 more people who've been role models for me. Vera Rubin, the discoverer of dark matter in galaxies. I was fortunate enough to have her as a mentor, not an official mentor, but she and I were working on competing projects to study dark matter in galaxies in Virgo class 10. Instead of sweeping me aside, she took me under her wing and we competed, but in friendly terms, and she became a mentor to me. In the center is Subramanian Chandrasekhar, famous Indian astrophysicist. He is my great-grand, not father, great-grand doctoral advisor. So I had 2 doctoral advisors, Jim Gunn and Tony Tyson. Jim Gunn's thesis advisor, doctoral advisor, was Guido Munk. Guido Munk's doctoral advisor was Chandrasekhar. Now, I met Chandrasekhar in Princeton. He came for a visit there, spent an afternoon with him, learned a lot from talking to him, I've learned a lot from his life's journey. And finally, on the right, you see the artist in me. This is an oil painting I did of Mother Teresa, but I didn't just paint her out because she was famous. I actually met her for 30 seconds, literally 30 seconds, no words exchanged. But thinking about her physical frailty, but the impact she had on the world, I still think about that every day, and I think about. I consider her a role model, not because she had any words for me, but because of the life she lived and the fact that our cosmic journeys intersected for 30 seconds, literally for 30 seconds. This has inspired me to really think about people. I think about all the people who've shaped my journey, and I want to, in some small way, provide opportunities for young people. We have a very strong focus on young people who don't have the kind of resources that my daughter had growing up in Silicon Valley, or many of my colleagues at the university. Their kids have a lot of opportunities because their parents are in an institution of higher learning. In Silicon Valley, I see a lot of people with privilege. I'm very focused on BIPOC students, Black, Indigenous, people of color. I've been really trying my best to connect to Indigenous communities. I went to a conference recently in Palm Springs, the American Indian Science and Engineering Society conference, their annual conference. That was a life-changing experience for me. I've been working with Native Hawaiian students. I am looking to go to Alaska in December to work with Native Alaskan students. Been working with students in Africa, working with students in India. Many students in India, including students who are really the poorest of the poor in the direst circumstances, children from slums off the streets of Calcutta who are being provided for by wonderful organizations. We're partnering with them. So this is part of what we're calling CREST, Creating Equity in STEAM. STEAM is science, technology, engineering, art, and math. This CREST logo is something I designed. This is part of my artistic inclination. This is a C. This is an R-E-S-T. It's no coincidence that there are 3 equal to signs in this logo. It's really about working towards equity in STEAM. We run a bunch of programs under this CREST umbrella. Shadow the Scientist is this logo over here. But we have a graded approach for bringing students into into science. Now, this is a snapshot of our team as we were. Oh, you share the same birthday as Stephen Hawking, Bill. That's wonderful. That's wonderful. So Sierra Schneider, Anand Lalria, Amanda Quirk, Christy Toll. We are soon going to onboard Abby Davis. We are working together on this. And it looks something like this. What we are trying to do is written out in horizontal tiles. I'm a big Scrabble fan. So what's written out horizontally is what we're trying to do, creating equity in STEAM. And what's written out vertically is how we're trying to do it. We're trying to do this by engaging young people and teachers in critical thinking in the context of open-ended research. Critical thinking can be anything. Critical thinking happens in every discipline, from art history to anthropology to astronomy, psychology to physics. And we want this to happen in the context of open-ended research while students are being mentored by some of the world's experts in those fields. That's what CREST stands for, creating equity in STEAM. But really the vertical letters tell you how we are trying to do this. Now, we're doing this in a graded way. And if you want to learn how to swim in the ocean, you better dip your toes in the water first and see if the water temperature feels right. And if the people in the water seem like they're having fun and if they feel like they're welcoming. So Shadow the Scientist is that first step. We want young people to see what today's scientists look like, what kind of work they do. We want to see them. We want young people to eavesdrop on our actual work sessions to see how work gets done and what problems we solve, how we interact with each other. Are we nice to one another? Are we welcoming? This is important. We can't expect someone to plunge in until we build trust. After a student dips their toe in the water, takes part in these sessions, we run these, by the way, we run Shadow the Scientist now of order 1 or 2 times a week. Every time I have time on the telescope, my colleagues have time on the telescopes. Right now, Gemini telescope in Hawaii has taken part, Subaru in Hawaii has taken part, Keck has taken part, Keck 1 and 2, and the Lick telescopes here at Mount Hamilton, California. So 4 different observatories have taken part. More and more observatories are signing on. This is something I started during the pandemic in November 2020. In less than a year now, 4 major observatories in the world are taking part. Many scientists are taking part. Once a student decides this is fun, I want to do this, they want to learn the swim strokes using that same water analogy, and we teach Python, a programming language, in the context of astronomy research. And one of my colleagues in the molecular biology department, he's now doing a postdoc in Chicago. He was a grad student in Santa Cruz. He teaches R, the programming language R, in the context of research in computational biology. So these are these 2 programs. One's called PR, one is called Recom Bio. Once students learn these techniques, they can take a deep dive. The Science Internship Program is something, again, I started this in Santa Cruz in 2009 with 3 students from one school in the Bay Area, from the Harker School. In 2022, there were 326 students from 100 different schools, 140 different schools. We had 66 international students. We had 30-some students from out of state. It's become this huge program, deep dive, high school students doing research, open-ended research, mentored by PhD students, working super hard for 10 weeks of the summer. There's another program that my colleague Annette Lee runs, and this is something called We Are Stardust, which is a project at the intersection of art, culture, and STEM. Sort of really an integration of these 3 things. After you take the plunge, we have, after a young person takes the plunge, we want them to pay it forward. We want them to engage other young people. We have something called the Global Sphere Network. Sphere is a backronym, STEM programs for high schoolers engaging in research early. It's a worldwide network that we started here at Santa Cruz. Alumni buddies are students who act as buddies, high school students who go through the Science Internship Program and then serve as buddies for students who are just a year or 2 younger than them, or maybe the same age, but haven't done the program before. We follow the trajectories of young people as they go through our program. We have teachers who take part in SIP, Science Internship Program. We have a peer-to-peer college and career network, and we have community college students who take part in SIP. So this is what we're doing today. Thank you.